So today what we're going to talk about is we're going to start talking about a way to figure out the area under a curve, which is one of the fundamental problems in a calculus class. So up until now, one of the fundamental problems in calculus that you've been talking about is how to find the slope at any given point and to how to find the equation of a tangent line to a curve. So now we're going to start working on the other side of the problem, which is how to find the area under a curve. So let's just draw a general example question. So say you had a curve like this, and you wanted to find the area under the curve. The first way that we're going to learn how to do them is using summations. So that's why before you learn about area, you have to learn about all of those summation rules. And what we're going to do is we're going to just divide up this into even amounts of rectangles. So if I had better drawing skills, they'd all be even. So since they're all on the x-axis, all of them have the same, and they're all supposed to be equal. They all have the same width down here of delta x. And so now what we can do is we can draw straight up to our curve and then draw over and draw rectangles in. So if we draw all these rectangles in, we start seeing how we're filling in this curve right here. And so now, if we were to find the area of all the rectangles, so if I were to shade in the rectangles to find their area, you can see that I'm shading in almost all of the space under the graph. So the first way that we're going to learn how to find the area under the graph is to just make these rectangles and then find all their areas and sum them up using the summation formulas. So one thing that's important to know is all of these tick marks we consider like this to be x1, x2, x3, x4, x5, and x6. And so all we have to do to find, so we know that the area of a rectangle is its width times its height. So when we're drawing area to find area of the rectangles that are drawn under a curve, the width is always this delta x. And then if we notice, and we'll use a different color, the height of each of these rectangles at these red points is if you draw over and mark them off, they're really just the function values at these different x values down here. So this is really just f of x1, f of x2, and so forth down the line. So to find the area, you just do delta x times f of xi. So whatever rectangle that you're in, you just want to multiply by the height of the rectangle, which is going to be represented by that function value. So now that we've kind of seen a general picture, we can talk about the formulas. So to find the area under the curve, you do the sum from 1 to n of the function values at each xi, which this is the height of your rectangle, and then times delta x, which is your width. Now you might be saying, what's your delta x? Well, whenever we do area under a curve, we're always given an interval of the x-axis to look at. So the closed interval from a to b. So delta x is always just going to be your b minus a. So this is going to be the length of your interval. And then you're just going to divide it by n, which is the number of rectangles. And then you might also be saying, how do I find xi? Well, xi really depends on your graph and if you're using what we call LRAM or RRAM, which those are some weird things. So before we move on to the next slide, another name for this is called a Riemann sum. So that might be one thing that you hear in your book. So use a Riemann sum approach to find the area under a curve. That's all a summation is. It's called the Riemann sum. So now we have LRAM versus RRAM. So LRAM just stands for left Riemann approximation method, and RRAM is just for a right Riemann sum. So if we draw that generalized picture that we had again, and now we'll just do 4 intervals. So LRAM just means that you're going to use left endpoints. So when you split them up into this 4 different rectangles, you're going to go to the left endpoint of each interval and go up to draw your rectangle. So you're going to draw up first and then over and go down. Then your next endpoint is going to be here. So as you can see for this one, we have what's going to be called an upper sum, because the rectangles go over the curve. So if we shade that area in, so we call this one an upper sum for this case. It's the left-handed sum is not always going to be an upper sum, is when rectangles go over a curve. And it's just because you're going to have more area for rectangles than you will under the curve because they go over. Whereas when we do right endpoints, just do the opposite of when you do left endpoints. So you're going to split your interval up into however many rectangles you have, and then you're going to go to the right endpoint of each one, draw up, and then over to form your rectangles. So for this case, we're going to have what's called a lower sum, because the rectangles are all under the curve. So again, it's not always going to be the case that a right-hand sum is going to be a lower sum. If we had a curve that went like this, for instance, and we did the right-hand sum, we would actually get an upper sum, and we would have the opposite then. We would have the lower sum being for the left-handed curve. So that's a little bit confusing, but we're going to see how that works out in the integral, in the example rather. So we're going to find the area under the curve from the point 0 to 2 using both LRAM and RRAM approach. So we're going to do LRAM first. So the first thing you want to do for these types of problems is you want to draw yourself a picture, because being able to see where your rectangles are and see how this splits up is going to help you out. So we are doing the function f of x equaling x squared. So I already have the graphs for you on your screen. And we're only doing the interval from 0 to 2. So we just want to look at the graph from here out to here. We'll even just drop down this green shaded line. So we want to find the area between those two green points. And so if we're going to do LRAM first, the first thing you always want to do for your sums is split it up. So the problem, I didn't write how many rectangles to use, but let's use n equaling to 4. The problem will usually tell you how many rectangles that you want to use. So the first thing you want to find always is delta x. So delta x is always just b minus a over n. So b minus a for us is 2 minus 0 over 4, which is just going to equal 1/2. So that means every 1/2 we go between 0 and 2, we're going to put a dash. So we're going to put a dash at 1/2, 1, 1.5, and 2. So those are our intervals, or our xi's. So this is going to be x1, x2, x3, and x4. So now if we're doing LRAM, we're going to go to the left endpoint of each one, and then go to the curve and draw over. So this one's just going to be at 0. Then we're going to go up here and up here. So for this problem, this is going to be a lower sum, because all of our rectangles are under the curve. So if we shade them in, we can see that we have leftover space between our rectangles and our curve. So we're not going to quite approximate completely the area. And if you were to let n be bigger, like if you let n be 8 or 12 or 16 or 20, anything like that, the more rectangles you have, the closer your approximation will be. So now what we have to do is we have to set up our sum. So our area for LRAM is going to be the sum from I equaling 1 to 4 of f of xi times delta x. Okay, so now you might be saying, how do I go about finding how to do my xi's? So we want to do, whenever we plug into here, we want these red dots to appear on the curve. So, because these are where the heights are coming from. So we want those heights to come out in our f of xi's. So a lot of the times the formula you'll use, it depends on if you're doing LRAM or RRAM. But what you'll do is you'll do f of a plus, and then if you're doing LRAM, it's usually I minus 1. And then we'll just put in our delta x as 1/2. And now you might be saying, why is it I minus 1? So think about if you plug in 1 for I, which is the first starting point, you really want to get it back at x being 0. So if I just plugged in I of 1, I would get my 1/2 back. Oh, and there should be a 1/2 here. So because I want 0 in here, when I plug in 1, I want to get 1/2 times 0. So I need to put the I minus 1 in there. Because now if we plug in for what we have, this is just f of a is 0. So we're going to 1/2 of I minus 1. That's inside of our function, times 1/2. So whatever you put on the inside here, you really just want to play around with it until you get out the x values that you want if you plug in each consecutive value of I. And I'll show you how to do it when it's RRAM. So now what we're going to do is we're just going to start plugging in. So the first thing we're going to do is we're going to pull the 1/2 outside of our sum, this 1/2 here, because it's just a constant. And now we don't want to have any f's in there anymore. So we're just going to actually plug whatever is in here into our function. So we're going to do 1/2 times I minus 1 all squared. And when we square that out, we get 1/2 still out here. And going from 1 to 4, 1/2 squared is 1/4 times I minus 1 squared. So what we're going to do now is we're going to bring out this 1/4, which is going to make this a 1/8 on the outside, times the sum from equaling 1 to 4. And we actually want to square out I minus 1 because it's going to make it easier for us to apply our summation rules. So I minus 1 squared is just going to be I squared minus 2I plus 1. So now we're going to split up our sum and then use our summation formulas, just like we were doing before. So 1/8 bracket I going from 1 to 4 of I squared minus 2 sum of I going from 1 to 4 of I plus sum from 1 to 4 of 1 and bracket. So I already went ahead and pulled that 2 outside of the middle sum just to save us some time. So now all we're going to do is plug in to our summation formulas and figure out what we're working with. So I squared is just always going to be 4 plus 1 times 2 times 4 plus 1 all over 6 minus 2. Formula for I is n times n plus 1 over 2. So it's going to be 4 times 4 plus 1 over 2 plus summation of a constant is just the constant times n. So we're just going to get 1 times 4 or 4 there. So now we're going to just get 1/8 times 4 times 5. 2 times 4 is 8, so we're going to get 9 here, all over 6. Minus, we're just going to cross out these 2's. We're going to get 4 times 5 here, plus 4. So we're just going to keep simplifying, so still with the 1/8 out front. Now let's do some cancellations in here. We can divide the 4 and the 6 both by 2 and get a 2 in the top and a 3 in the bottom. Then we can cancel the 3 with the 9 and get a 3 up top. So when we do that, we're going to get 2 times 5 times 3. So we get 10 times 3, which is 30, minus 20 plus 4, which is just going to be equal to 1/8 times 14, which is going to be equal to 14 over 8, which we can simplify to be 7 over 4. So that's our LRAM approach for the area. And so now we want to do an RRAM approach. So we're going to just redraw our graph real quick. So for RRAM, your delta x's are always the same, whether you're an RRAM or LRAM. So RRAM. So delta x is still going to be 1/2. So we're still going to split our interval up the same way, except now we're going to do right-hand approach. So we're going to go to the right-hand endpoint and draw over to make each of our rectangles. So we can see from the picture now that we're going to have an upper sum for this function. Okay, so when we do that, now we just have to set up our summation. So for RRAM, we're going to have the sum from I equaling 1 to 4 of f of a plus your formula is always n delta x. I'm sorry, not n delta x. It's always just going to be plus delta x times I for RRAM, and then delta x on the end. Because if we plug in 1 now, we want to get 1/2 out for the first one, and then 1 out when we plug in I equaling 2 and so forth. So this is just going to come out to be the sum from 1 to 4 of f of, this is a 0, plus 1/2 I times 1/2. So we're going to go ahead, pull our constant out front, and just start using our summation formulas here to break this up. So we're going to plug 1/2 I into f and get that this is 1/2 sum from 1 to 4 of 1/4 I squared, which if we pull out that 1/4, we're going to get a 1/8 out front again, times the sum from 1 to 4 of I squared. And now we can just plug in for our formulas. We don't have to split it up. So I get, oh, sorry, not 1/4, 1/8, whoops, times 4 plus 1 times 2 times 4 plus 1 all over 6, using that summation formula for I squared. Now we're just going to simplify. So we're going to get 1/8 times 4 times 5 times 9 all over 6, which if we do some cancellation between our numerator and denominator, we can do 4, this is going to become a 2, this is going to become a 3, the 3 can cancel with the 9, which becomes a 3. So we're on the inside, we're going to get 2 times 5 times 3, which is just going to be 30. So we're going to get 1/8 times 30, which is just going to be 15 over 4. So that would be your RRAM approach for finding the area, which if you notice, 15 over 4, we already determined that RRAM was going to be the upper sum, and we can show that with our answer because 15 over 4 for the RRAM was much larger than the 7 over 4 for the LRAM approach. So I hope this helped today. That's just a simple example of how to use the Riemann sum approach to find area under a curve. So thank you so much for watching. Have a great rest of your day.